Hi, my name is Sergio and I've been working on the Kino Row. And what the Kino Row is this device that we're going to use it as a wearable that you put around your arm. And what it has is a different sensors and a chip that connects through or via Bluetooth. We have different sensors such as the accelerometer, gyroscope, and magnetometer. And all this is connected to a 32-bit ARM Cortex-M processor that is used to connect through devices via Bluetooth. So this is the Kino Row 1.2. As you can see right here, it says cut out because this piece is going to be cut out so that the AAA battery can fit inside of it. From here you can see the different sensors, the magnetometer, accelerometer, and gyroscope, and they're all connected all the way over here to the ARM processor. So the main trick on this one is kind of squeeze as much space as possible so that it reduces the price of the board, because it all depends on the size of the board is what varies the price. And then went to the software FreeCAD in which I designed the case for it. So as you can see, it's got the overall shape. You can kind of see some indentation right here and here, which is where the battery or the holder for the battery is going to be at. You can kind of see little indentations here for the LEDs, which are located here and here. The upper case, you can kind of see the latches that I had to develop so that, you know, it stays closed when you close it.
Do you have to take into account how close you have to put the leads together, or how closely?
Yeah.
Them together?
After a while, I think Nick kind of passed down a little bit of his experience, or his wisdom, but I use MATLAB to pretty much crunch numbers and keep these spacing roughly the same distance apart from each other, a certain amount of distance. I know that, say like this device right here, I kind of actually had to shrink the pads just a tad bit so I could squeeze the wires in between. What's the question?
What was the most challenging part of designing this board, PCB board?
It was definitely squeezing everything together. Because as you can see, first I started off with this being much larger, and I kind of, you know, I had the devices here, and from there I'm just like, alright, I know I have to have this many wires going through. So I kind of did some, I don't know, some, what do you call it, some fake wires, I guess, just to kind of get the distance right. And then from there, kind of trim it down, and then next thing you know, you realize that once you get a bunch of them connected, there's more wires you need to go through. I'm getting it, I'm about 80% done, then you realize you gotta move another wire from one side to the other, and then you realize there's no space, and you have to start moving stuff, making things tunnel through, and things like that. So that was probably the most time-consuming and annoying and difficult. I don't know, what was your question? Was it most annoying or more difficult?
Good.
I'm Jaesung, and I also did PCB design with Sergio, and so this is like the other half of his board. So you saw how he had those pads on the bottom layer. That corresponds to these pads over here, where we would have pogo pin and we solder it on, and then we would kind of sandwich the boards together, and that way we would have connections. And mainly this board has a UART to USB, so that it's able to communicate. And so I will get signals from Sergio's board, and it will communicate with my UART USB.
Hi, I'm Kenneth, and I'm working on the Kino firmware. And a big part of developing this firmware is dealing with the I2C bus. And the I2C bus, it's an interface that allows the slave device to communicate with the master chip. In our sense, it would be the different sensors would be the slave, the accelerometer, gyroscope, and magnetometer, communicating with the Nordic microprocessor. And how the data is exchanged through the I2C, it utilizes a two-wire interface. The first wire would be the serial data line, and the second, serial data line, and that is used to transmit or receive data. And the SCL, or the serial clock line, controls the data transfer rate between the master and the slave. When you look at the far left, that's where it starts, and it's indicated by the start bit or the start condition. And the reason it knows it's a start bit is because when the SGA transitions from high to low, the SEL line goes low, and that's the reason why there's kind of like a slight delay between the two. And once that happens, it indicates it's a start condition. And once this is received and both lines are dropped low, the whole the interface is considered to be like busy. So once that is set, then the SDA transmits the slave address, which would be the device address or the sensor. And once it sends that address, it's the first 7 bits that it transmits the address, and the last 8, the 8th bit determines if the master device wants to read or write from it. The gyroscope, the accelerometer, and the magnetometer, they each have their own designated address that's predetermined from the manufacturer. And yeah, so you just take that address, send it, and be like, I want to read it from this address, from this device. What indicates the stop condition is if the SGA transitions from low to high, and that's also why there's like kind of a delay also between the two lines. The accelerometer has 12 bits of data. It transmits 12-bit data, and gyroscope 16, magnetometer 16. And how I'm pulling this off of, I'm storing it into an unsigned 16-bit integer. And how all 3 of these work, they kind of store them into 2 different registers. One register would have the most significant, for example, x-axis, and the following register would have the next 8 bits, or the next 8 least significant bits. And I would just combine them together and then figure out how to convert the different data. And I'll go through how. And this is an example of like how I converted some of the data. For example, the gyroscope at a range of 500 dps, which is degrees per second. There's 1/60 degrees per second per least significant bit. Accelerometer, I had to convert it from the raw data to G's or meters per second squared. And the magnetometer, you get the raw data into Teslas. So, I will send the letter A, which indicates that I want to pull data from the accelerometer. And let's have the board oriented so it's flat. So what should happen is the z-axis should get about 1 G because you have 9.8 meters per second pushing down on it. And then the other axes should be close to 0 because they're not being pushed down on. And so let's send that A. Yeah, so you see accelerometer X, that's, you divide it by 1,000, so it would be about 0.0031, and then 0.0008, and then Z has 0.945, so it's close to 1. And then, if I want to read from the magnetometer, then I type in an M, and so I type in an M. And how I have it split up right now, kind of purposely did that for today. I have it split up so it's in MSBs and LSBs. So you can see how I have to pull from different registers to get each bit, like the 8 bits and 8 bits for each axis.
Alright, ready?
Yeah.
Go.
Okay, I'm Ben, and I've been working on the analog to digital converter in order to find the voltage of the battery. And first of all, in order to do that, I had to implement some kind of voltage divider. And the reason for that was because the maximum battery voltage comes out to 4.2, but the maximum that the chip can take is 1.2, or else it'll blow out. So in order to do that, I had to find 2 resistors that would give the best resolution also, and I'll explain what that means later.
Cool.
On this code here, you call that, and it'll do the conversion, it'll run the conversion, and it'll automatically hit this interrupt handler right here when it's finished on its own. And then I implemented some things for debugging that would turn on like an LED or something if I'm getting a correct kind of number, I suppose. And right now I'm working on sending it through Bluetooth, which I can show you, using the NRF UART app on my iPhone. As you can see here, it is connected to my Kino mote. So if I can just, all I have to do is type in a V, I send a V, and it'll give me a number, which will be the voltage. Our processor just doesn't have a floating point unit, so therefore I had to multiply it by 10,000 in order to see to a certain accuracy, I suppose. And you can automatically implement the decimal by yourself.
I'm Danny, and I've been doing Bluetooth firmware. And so what I've been doing is creating services that work and allow data to be transferred back and forth between a device like this and a phone, and have it be readable on an app. The app general access protocol, it specifies the device roles, so it says which one's which pretty much. It like specifies procedures for discovering devices, and services are, I'll get into services in a second, but yeah, it just pretty much manages the connection between 2 devices. And this would be considered a central device, and this can connect to a whole bunch of devices, a whole bunch of peripheral devices. And the peripheral device can only connect to one central device at a time. The entire profile could be considered like an app, an entire app. A service could be considered like a temperature service, where a characteristic of that service would be the actual value of the temperature. And it can also have drink values and all that. Okay, another important part of actually transferring data back and forth is that the server, and this would be considered client in this case, the client can trigger, so it can ask for information, it can ask for data. So you can pretty much request data, and this would send a response. So it could send the data back or any kind of response back. And then the server can also display data on its own in connection intervals, where it would just advertise it, or not really advertise, but just transfer data. And there's 2 different kinds of notifications and indications. The notification will send data, period, like regardless, it'll just send it. And the indications are, it'll send data, but it needs some kind of confirmation from the device saying, okay, we've accepted it. And you can control the power at which it transmits. So like, we ran tests, and the greater the transmit power, the farther it can go. And still, there's a limit on how far you can go, of course.
But you can't
You can't control how strong the signal is. So that's what we're doing right now. We're going to, we have 3 beacons, so it's pretty much 3 little like antenna type things that are going to measure the transmit power.
Alright, so what are you doing right now?
So these are Bluetooth beacons. It's pretty much emitting a Bluetooth signal. Here's a chip that is the responsible for programming this device, and the antenna is what's emitting the Bluetooth signal.
Okay, so you have 3 of them?
Yeah,
Looks
so I'm
like.
placing them at different parts of the room.
Alright, and Danny, what's the purpose of this?
you can read the signal from each beacon here.
Yeah.
So ideally when like say this beacon, the farther I get from this beacon, the signal strength should drop, and say I walk closer to another beacon, that signal strength should increase.
We're pretty much gonna get at is if the signal increases, that means you're getting closer to the device.
Mm-hmm.
So with 3 different signals, they're gonna vary. From there, we're able to triangulate where in the room you'll most likely the device will be at.
Alright, my name is Ricky.
Hi, my name is Marzhan.
I'm Kevin Wang. Hi, I'm Garman Chang.
And we're the Kino sensor fusion team. Our project was to take in gyroscope data and convert it into orientation data. And so once we're done, we would have our data make our model do this. The data comes in through the cell phone, and what it does, it collects acceleration, gyroscope, magnetometer, and orientation data, which we will use to check whether our gyroscope integration works. The phone is sampling at a certain frequency, and if we want to send in data that needs to be sampled at, say, 100 hertz or something, then we would need to figure out data points in between the time stamps that we gathered from the phone.
So I worked on the part where we have to integrate the data. So first we get this data from what Ricky did. Ricky interpolated it. We see interpolated data that Ricky worked on, and 4 columns with the timestamp in microseconds and XYZ components, which are in units of radians per second. Okay, this is the block that does integration. So it gets each XYZ component from the data and multiplies it by the timestamp. And from there we go here, and that would give us the rotation angle, X, Y, and Z.
Okay,
You
good.
can go.
Alright, so I'm talking about the quaternions. So from the rotational angle, we convert it into quaternions, and then through that, through the quaternion multiplication, we add up all the quaternion values, which means that since it rotates once, it would give us an X value of 360.
Well, I essentially wrote a code where it takes in the orientation data, and then we convert the quaternion values to angle axis. And once we did that, we essentially get the rotating figure here. So as you can see, it rotates how we want it to rotate. And my part was essentially just testing whether Ricky's code would work or not.
I'm Aaron, and this is Mario. We're the data collector too. We're collecting data for like different exercises and actions that people do in the gym, or like basic training stuff.
This, which is and then we just press start, and then when you move, it collects data as you move. And after this, we get the data in the computer. Yeah. This is microseconds. And we have the X, Y, and Z acceleration. And now we got another thing, which is the synchronization, because we're also videotaping this, right? Like you want to see your actions and match it up with the data. So as before we start our exercise, we gotta do this, like the phone strapped here, and we want it parallel to the ground. So we just stretch our hands and make the phone parallel to the ground, and then we make a jump. And to get the when you're jumping, since the acceleration on Z direction is measuring on
normal force. As your halfway is free falling, that should be 0. Your acceleration on the z direction. And we look at the video when you're like walking back halfway. Then we look at the data and see where it's like the most 0 at the beginning. And that's how we match up the two things, the video and the data.
Alright, I haven't actually thought this over what I'm going to say, so let's see how this goes.
I was just wondering why his
Alright, so basically what I do, I get some summaries. So we have you guys making, Sergio's making the device with Jaesung. Then we have like the firmware guys. Then we have the Simulink guys working on the fusion algorithm to take, the data from the sensors and process it and get orientation, which then goes to like the data collection people who collect the data, and they basically give it to me. And so what I work on is something called machine learning. This is how you teach a machine to think kind of like a human. Specifically what I do is neural networks. And so what they found is that the human mind can be simulated in a way, in the sense that we have neurons. They're all interconnected in a very complex way. And over the past couple of years, we figured out how to mimic those interconnects and how to train them in a similar way to how a human brain works. So the stages you normally go through is, you'd say, take some data, and that data might be like the push-ups, sit-ups, and let's say like a press. Each of these are labeled pieces of data that the machine will look at and try to figure out which of these is occurring at the given moment, right? I don't expect you guys to understand all this. I'm just going to actually go through what's done. So the first step is you take this, this is actually a 200-dimensional space. It's a whole bunch of data points, and kind of similar how, let's say you just look at, you do like an interpolation, kind of like you guys have worked with. You have like maybe a line or a parabola. What a machine learning algorithm is learning to do is find a nonlinear way of mapping points almost, but in very high dimensional space. So this is not something you can visualize yourself, right? Anyway, so you have these datums, and it essentially has, say, 200 points of time where something's happening. You would take these, you'd run something called PCA, and what PCA is it reduces the dimension of data by finding which of the dimensions, maybe there's not a lot of variation in that dimension, maybe it's redundant. And so this first step basically removes any redundancy in the data. At that point you'd have maybe, say, like 50 dimensions, right? That actually contain some information about what you're doing. After that, you would do something called unsupervised learning. And the example I like to think about with this is, let's say you're trying to learn French, right? You haven't gone to France yet, you don't have a French book, but you can listen to like the French radio station or listen to like French TV, and you kind of get an idea for what French is, even though you have no idea what they're saying. So this is the same thing that happens in a neural network when you do unsupervised learning. And essentially it looks like this. So you have, these are neurons, and so these are your input neurons. This is where you put the sit-ups and push-ups and stuff. So this might be, acceleration. This might be like the gyroscope. This might be, the magnetometer. Just a whole bunch of different dimensions to what makes that motion. And there'd be, say, like 200 of these, right? These are all interconnected to another layer, and this is where the neurons come in. This is like your brain. All your neurons are kind of connected. And so what you're telling, essentially in the unsupervised learning, is you're trying to get it to recognize the identity basically you want it to replicate the input on the output, right? While also having very few neurons in between. And so what that essentially does is it forces the neural network to compress the representation of what it's looking at, right? And our brain kind of does this. It's kind of like how we generalize. So when I'm looking around, I'm not seeing everything at once. I'm kind of generalizing, like, that's a chair, like those are edges, that's red, that's white. I don't see like, okay, that's like RGB, 244, 50, 30, or anything like that, right? That's too much information. So this is kind of a compression step that we do automatically. Even as babies, you start to do this before you can actually see, right? And so this takes it down even more. So in the beginning we had PCA, which compresses it down from say 200 to 50. We have this, which even compresses it down more. So let's say that we now take it down to 10 dimensions. You can kind of look at it as. At this point, we actually take our push-up, sit-up, and press label data. And if we look back to our French example, now we actually go to France. We look at a French dictionary and we learn, oh, this, gâteau is cat. Or that's not French, but we understand what the words mean. And because we have this kind of compressed representation for like all the different nuances of French, it's much easier for us to understand the different words now that we have them. So what you do in that case is you would have, and this is all learned in the previous step, we then add another layer, which would say be like push-ups, sit-ups, press, and etc. Basically for anything we want to recognize. And what we do is we would take, say, some of Mario and Mario's data and input it here. It would propagate through all of these neurons. It'd come out at the end, and let's say instead of detecting it as push-up, it detects it as sit-up, right? What you do is you back-propagate this error through all the nerve endings, and you correct them. So maybe like this connection right here was most, actually maybe this connection right here was the main cause for it getting this incorrect, right? So it would modify this guy, it might modify these three guys, and it modified it in such a way that it tries to make it more look like a push-up, right? And basically after iterating over this for thousands of cycles, each of these neural connections get tuned more and more until you can input, say, a sit-up or a press, and on the output it'll tell you sit-up or press, right? And this is actually how the brain does work. So are there any questions on that 5-minute intro to machine learning?
So it's more like a statistical model of like trial and error.
Kind of, yeah.
Like fine-tunes it.
Yeah, it's a very complicated statistical model. Thing is, we can't understand how it works. We just know it kind of does work. Right, it's like you try to understand your own brain, you can't quite do it, yeah. Mm-hmm. Kevin, you have any questions?
No.
Okay, good. Right.
Alright, so my name's Kevin, and I helped all three of them go through the process of learning QML, and I had them use list view and images and image animations and everything like that, just to get them familiar with manipulating objects in Qt and in the QML markup language. We want to integrate usage of the mode into the interface with the PowerPoint. So we're going to use the use of the slideshow and doing this all in QML versus PowerPoint is to kind of demonstrate everything that everyone has done. Because we're going to be using the mode, which is going to be like working via Bluetooth, and we're going to use gesture recognition, which is also being developed by Mario, and I actually don't know your name.
Aaron.
Aaron. I don't think we've met. Kevin, nice to meet you. So yeah, we'll be using those and 3D modeling to kind of show off using the moat attached to like an arm, and just go through all the slides that'll show off the code and show off the data and everything.
Okay, cool.
Like that.
And so this is kind of like a little demo thing you guys have done just to learn QML. So in the future you can do more sophisticated stuff. Okay, cool. So jump into it.
So yeah, what I did, just you can scroll down and see kind of like which item you want.
Mine has the same properties, allowing me to scroll through my elements, my list elements, and send them over to the right side by using keys on pressed commands. Just clicking the other direction, I need it reversible.
Oh, my name is Guillermo. I'm also in the Qt project, working with QML.
Yeah.
And all the other ones just do specifically what they say. Just as an example.
Okay, great. Good job, guys.
Oh yeah.
Make it like a quick 30-second thing. Yeah.
I will tell you about gyroscope. You talk about interpolation.
Okay. So I'm looking at your screen. Just tell me what's happening.
I'm working on the gyro update function that will take interpolated data and integrate it, and from there you would convert it to coordinates, and you will rotate the box.
Okay. And what did you work on earlier?
I worked on interpolation, data interpolation, where I would enter in a certain sampling frequency, and the program will generate data values in between the data that's being collected. So I wrote functions that did that and would output a file with the interpolated data values.
Okay, cool. Sounds good. And what have you been working on, sir?
I've been working on data collection.
Yeah.
For movements such as like push-ups, sit-ups, and jumping jacks. Just seeing how the correlation between the x-axis and y-axis acceleration, as well as the elevation and stuff.
Okay, cool.
So we have been taking data collected by data collection group to input those values into Simulink, and after that we would have to have it rotate the model.
Yeah. Like Kevin, you want to show me your slightly glitching out thing?
It is a work in progress.
Right now it's not moving.
Well, it takes a while before it starts moving. Yeah.
Oh, there you go. Is this in Simulink?
Yeah.
Yeah.
It's beautiful.
Yeah.
It'll be more beautiful later.
Yeah. All right. What are you working on for the past month?
Trying to get a custom Bluetooth low energy service.
Yeah, so what have you done? Have you made so far? You made a couple of things, right?
I made a bunch of services so far, like TX Power service, the Bluetooth service, Immediate Alert service, Immediate Alert Client service. Just a bunch of Bluetooth services that make up the whole Bluetooth profile.
Yeah. And what are you doing right now?
Right now I'm doing a custom Bluetooth service for the accelerometer data, transfer accelerometer data,
Okay, cool, sweet. Alright, and the cute guys and girl. Just give a summary of what you guys have been working on the past month. I guess your goals.
So they've been working on learning the Qt language, building a few slides, using
talk about them.
Yeah. I've been working with images and a lot of image effects. So how to import images and what to do with them.
Yeah.
Make it blur, make it move, all that stuff.
Okay, cool. Jen?
I've been working on like the different kinds of transitions. It's like ultimately like when we do the slides, the cool parts, you know.
Mm-hmm. The fun stuff.
God dang.
Dude, just stop. Oh my gosh, dude.